going to start then. So I'm going to continue talking about discrete walks. We don't need that. And so I want to talk about perfect state transfer in discrete walks. Now, the general principle is that anything to do with discrete walks is always more complicated than the continuous analog, but we'll see that as we go along. So the problem is, well, when we talk about continuous walks, we're looking for transfer from one vertex to another. We have vertex states, that's fine. It seems, I don't know that we have an interesting example other than simple permutations of discrete walks where we get perfect state transfer from one arc to another, the arc reversal walk. Okay. Now, the situation where we do have examples is what I'm going to describe next. So I'm going to, the rough idea is instead of trying to get a transfer from one arc to another, you decide you want to get transfer from the set of arcs on one vertex, leading one vertex, to the set of arcs leading another vertex. So you're getting transferred between two sets of arcs. Now, this is no particular problem. So now you just got to write down your density matrix. And so I'm working as follows. I'm saying I've got a unit vector in C to D, and I'm going to define this guy to be E sub U transposed Kronecker ZZ starred. Okay, so this is a pure state. Okay, in fact, you can write it as EU tends to Z times the transpose of EU tends to Z. So it's a pure state. So at least we're not going to run into, I mean, you can talk about transfer between states that aren't pure, but again, that gets a little more complicated. And the interesting, okay, we're going to look at the arcs on the vertex. Now, in principle, we could weight the arcs on the vertex, but we've got no reason we don't know how to choose weights anyway, so we may as well just assume we've got the uniform weights on each arc, so each arc is equally likely in some sense. And so that means we're going to be using our initial state will be this. And the little lemma here says if you have transfer from this state to this state, then Z is actually 1 over root D times 1, the all ones vector. Now, I'm going to be a bit sloppy about my scaling in these situations, but it doesn't cause any problems. It doesn't cause me any problems anyway. If we get transfer, so this it's not too important, but it's kind of nice. It's telling us that things are working a little bit better than we might hope, and that's always a sign that we've got making the right assumptions. So we're going to assume that A's got a spectral decomposition as given, and that means that the corresponding transition matrix for the arc reversal walk will be given by this at this form. Now, and our assumption is that at time k, we have du1 going to dvz. And the key thing here is simply that because u is real, we're dealing with arc reversal walks, okay, on a graph. U is real, and this is real. And so since everything here is real, this must be real. And so that implies that Z is real. Okay. And now the all ones vector is an eigenvector. Well, it sticks by U. And so we do a quick calculation. And I don't think I'll go through it, but we have these two expressions. So what we're doing is we'll be computing the sum of the entries of dvz and du1. This is the all ones vector. And so for the dvz, we get just the sum of the entries of zz starred. And for the other, we get D. And then by Cauchy-Schwarz, we conclude that because we have, we get equality in Cauchy-Schwarz, and that implies that Z must be parallel to the all ones vector. And so that gives us the result. So the nice thing here really is that we're using it. It's interesting that we can still use the fact or play with real states. Okay, so when we're working with continuous walks, the fact the states are real matter quite a bit. and it can still play a role in the discrete walks. Okay, although it's generally speaking, the states you're seeing will not be real. Well, I'm not sure that's true or not. In any case, our jargon is that if we get transfer from u, 1 to v, 1, then we say we have perfect state transfer from vertex u to vertex v. Okay, and so that's our definition of it. That's what we mean by perfect state transfer on the arc reversal walk. Now, there's no reason why you couldn't also ask for transfer between arcs, and that will come again later on. But I mean, the real issue is that we do not have interesting examples of perfect state transfer between arcs, but Harmony did find examples of perfect state transfer of this form, between vertices like this. So we have examples, and it's a natural enough concept. And I left as an exercise that if you get transfer from u, y to v, z, and y is real, then z is equal to y. So I'm not sure what use that is, but it makes an exercise. Okay, so perfect state transfer on arc reversal work, it's got a particular meaning. Okay, perfect state transfer is perfect transfer between states. But so what we're doing is specifying the states we want to work with. Now, I want to go, basically I'm going over one of the reasons that continuous discrete walks can be trickier than continuous walks. Now, for continuous walks, if we have D1 going to D2 at time t, and D1 and D2 are real, and you take complex conjugates, then D2 is equal to its own complex conjugate. Complex conjugate of u of t is u of minus t. Complex conjugate of D1 was D1 bar, but that's equal to D1, and u of minus t goes to u of t. So, and so we have this equal to this, and so then you move the u's over to the left-hand side, and so you've deduced it if you have transfer between real states D1 and D2 at time t, then you get transfer from D2 to D1 at time t. Okay, so we have this symmetry property, and that implies periodicity, and we can do a lot with it. So this is quite useful. But discrete walks, well, just sketch it out. So we're assuming now that D2 is equal to u to k D1, u to the minus k, so some k, and the D1 and D2 are real. Then we take our complex conjugates, and we get the D1 is u bar minus k, D2 u bar minus k, u to the k. Now, basically, this is all we get. I can't move things over, so I can't claim that on the same discrete walk I get transferred from D2 to D1 at time k. There is some sense in which if I run the walk backwards, I can get transferred from D2 to D1, but in some sense we knew that because operations in quantum, our standard operations in quantum physics are invertible. We don't get any. So the point is that if we get state transfer from one real state even from one real state to another, we don't necessarily get transferred back again, and so we don't get periodicity. Okay, that's just a general fact we have to live with. But Harmony proves a nice result. So we've got a transition matrix for the arc reversal walk on X, and got vertices U and V and X. And the theorem is that if you get transfer from U to V at time k, then you get transfer from V to U at time k. So we do get transfer in this case. Now, this raises a number of questions, but I'll come back to that. So this is the the proof of this is nothing like any of the proofs we do. It's not what you expect necessarily. We can't just play, silly buggers like this and get the and read it off. So we'll see how that goes. Now, to prove this, we need a characterization for perfect state transfer on the arc reversal walk. Okay, and this is again due to Harmony. So again, reminding you, we're dealing with a K regular graph. We're looking at the arc reversal walk. And the theorem says that we have perfect state transfer from U to V at time k, if and only if these three conditions hold. So first, that for each lambda, E lambda E sub U is plus or minus E lambda E sub V. And if both these terms are positive, there's an even integer j such that lambda's got this form, d cosine j pi. Well, it's got the same form in either case, with the j there, j even. And if they're opposite sign, then j is odd. So if those three conditions hold, you get perfect state. Then if they characterize perfect state transfer on the arc reversal walk. Okay, notice that this is pretty much strong co-spectrality. Well, it is strong co-spectrality. Okay, and now there hasn't really been much done about strongly co-spectral states for discrete walks. But in this case, so one consequence of this result is that if you get transfer from U to V, then U and V are strongly co-spectral. Okay. So the other comment is that notice that these three conditions are symmetric in the vertices U and V. So if these hold for U and V, they also hold when you swap U and V. And so that gives you the proof of the earlier theorem. That gives you the fact that if you get PST from U to V, you get PST from V to U. Okay. Now, the one question is that, well, so it holds for arc reversal walks. What other families of walks does it hold for? And in particular, the next easiest class is probably the bipartite walks we get from biregular bipartite graphs. So biregular bipartite graphs, the white vertices have one valency, the black vertices have another. So from that we get two partitions and we get two reflections and we get what we call a bipartite walk. Okay, and there are lots of special cases. And so it seems plausible that this result would hold for the bipartite walks in the biregular case. But Tina swaned off to Germany, so I can't make her do that. So, and well, okay, so leave it at that. Now, I just chose not to go through the proof of this. The proof's in the, I think it's in Harmony's thesis and certainly in our book. And I'll leave it at that. I decided I didn't, there are some messy details. You need to work out the eigenvalues of the transition matrix and the eigenvectors and the multiplicity so that you get vector recomposition. And it's not too bad, but it takes a degree of patience. So let me go on. So I wanted despite the fact that the discrete walks are, as I said, more complicated to deal with than continuous walks, there's a large degree of overlap. And so a lot of the concepts that we use for the continuous walks will carry over to discrete walks. I guess the first example would be strong co-spectrality, because we've just seen that happening, and that's involved in the perfect state transfer. So now there's kind of a reason for that, and maybe I should. Yeah, if we have a, no, I don't. If we have our transition matrix for, say, an arc reversal walk, if U is unitary, then that implies U is equal to X of I H with H Hermitian. I think I dumped that on you as an exercise. Now, the physicists call this matrix H a Hamiltonian. And in some sense, it corresponds to the energy of your system, but that's really about that. So every unitary matrix can be written as exponential IH. And so when we have U to the K, okay, we have that. So so it follows that we can embed our discrete walk in the continuous walk. Okay, we just take the continuous walk. We take the continuous walk using this guy as a Hamiltonian. Okay, and then if we look at it integer times, we're going to see the corresponding discrete walk. So every discrete walk can be embedded in a continuous walk. Now, why don't we do that? Forget about it. The problem is that in general, most unitaries, it's more or less impossible to implement them. There's too much. You've got a 100 by 100 unit, you've got 10,000 complex numbers stuff in there. So you don't really want to be working with things like that. And so when we're doing continuous walks, we choose H to be the adjacency matrix of a graph. Now that's in general sparse and we can implement it, so we're good to go. In the general discrete walk case, we're making assumptions, well, like two reflection walks. Now, two reflections can in general be, the reflections can be implemented easily. And furthermore, two reflection walks, we can do the spectral decomposition. So that's a nice class of walks. Okay, but the point still is that every discrete walk embeds naturally in a continuous walk. It's just that it may not be convenient to try and work out what that Hamiltonian is. For example, if I was feeling very nasty, I might ask you to work out the Hamiltonian for the arc reversal walk. I've got no idea what it is, but it's not going to be nice. Close that off. The other point would be, for example, when we talk, well, I'm going on to mixing in a minute, so we talk about averages. Well, I proved that for a continuous walk, if it visits a certain state, it returns to within a silent state infinitely often. Now, the proof of that, if you look at it closely, actually proved it for a discrete subwalk. Okay, so the discrete walk has the same property. If it visits a certain state, it returns to within a silent of that state infinitely often. And in fact, if you want a more complicated exercise, if you take the average mixing matrix for the discrete walk, which we'll be talking about in a moment, will be equal to the average mixing matrix for the continuous walk. Okay, so there's connections between the two. Okay, and one sort of consequence of this is the number of the properties that we use when we work in continuous walks can also be usefully applied to discrete walks. Okay, so enough of the sermon. So I'm going to, there are a number of things we can consider, but I'm going to consider mixing. Okay, and so, oops, I need to explain that. Okay, so we're going to be talking about mixing, which I'm about to define. And so we have the usual setup. I'm going to have an initial state D0, and at time K, I'm going to have a state D sub K. Okay, and so we define the average state to be this. So when we're dealing with the average states for continuous walks, we had an integral, a very similar form. Okay, and we denote the average state corresponding to D0 by D hat. And so we can go through, work out that if we have the spectral decomposition for the transition matrix, then this is equal to this mess, or equal to this, which is not so messy. Now the point is we can separate out the diagonal terms, the diagonal terms and the off diagonal terms. And now to get ahead of myself a bit, this is the part that matters, because when we average this over M, this stuff goes to 0. Okay, it's a bit messier than the calculation with the integrals, but it's and so I've got a few hints here, so that the point is the sum here can be written as in this form. And so this is 1 minus, say, zeta, a complex number of norm 1. This is 1 minus zeta to the k. And so then you work out that the average is equal to the diagonal part plus this. And then if you've got enough patience, you can prove that this part goes to 0 as k goes to infinity. We'll leave it at that. And so the conclusion is, if U is unitary, spectral decomposition is given, the average state of the discrete walk is given by this. Now that's the same formula as we got for the average state for the continuous walk, except I was using ER there for the idempotency. Okay, and so that underlies my claim that when you're working out averages, if you have a discrete walk embedded in a continuous walk, then the averages agree. And another remark is that if U applied to FR is going to be e to the I theta r times FR, because E sub R is the projection on the eigenspace. And so if we take U applied to the average state, we get a theta in front and a theta minus behind, and so we get this. So it follows that the average state, the zero hat, commutes with U. And if you want to be high flying, we can say that the map that takes a density matrix to its average is a orthogonal projection onto the commutant of the transition matrix. And so algebraically, that gives you some leverage, which we won't need today. But the point still is the average state. I mean, it makes sense if the average state shouldn't be changed by the transition matrix. You've got your walk has got an average. The average shouldn't be moving along as time goes. If you find that convincing. Now, so I want to get a formula for the average mixing matrix. Now, the mixing matrix for a continuous walk was U of t circle U of minus t, or UT complex conjugated, but so U of t circle U of minus t. So we want to work out the corresponding formula for the for the discrete case. And in this case, well, the other point is if you're using the mixing matrix, you're implicitly assuming that your initial states are vertex states. And as always in quantum computing, you measure with respect to the standard basis. So your choice of states are the vectors ER transpose, and the terms in your measurement, the projections in your measurement are the matrices ER transpose. So you have the same initial states and the same measurements. That's just what it is. But my point then is you're going to use the mixing matrix. You're effectively working with a standard basis. Okay, so the standard basis would be the functions. We're dealing with functions on the arcs. Okay, so let's choose an arc alpha in X. Okay, and we can. Well, first thing is probably after K steps starting from D0, the walk is on alpha. Well, you've got a state DK. You're measuring. You measure respect to the standard basis. So, well, as I said before, you're just pulling out the alpha diagonal entry of D to the K. Okay, so I did say when you're doing measurement on continuous walks, the probabilities you're seeing were just given by the diagonal entries of the density. And this is still true, and for the same reasons. And so this is the probability that we're on alpha, given that we started on D0. If beta is another arc, and we choose D0 to be E beta E transpose, so I wasn't making any real assumptions about the initial state here, but now I am specifying it. Okay, then you do a calculation, and you discover that the probability that you're on alpha after K steps, given that you started on beta, is given by this. So, I'll come back to that in a bit. So we have a concrete formula for the probability. If you start on the arc beta, then the probability after K steps you're on alpha is given by this. Okay, and we had similar formulas for the. So this is in some sense the analog of the mixing matrix. I could call that M of K. We'll come back to it in a bit. If we apply the spectral decomposition to this mess, then so we just expand U to the K alpha colon beta spectral decomposition ditto here, then you get this so you get E to the IK eigenvalue difference times FRS times FSB alpha. Now, this is pretty reach up and bite us in the backside from time to time. The thing to notice here is U is a unity matrix. U is normal. So the idempotent in its spectral decomposition are Hermitian matrices. Now, it's almost worth making that an exercise. It's easy to get confused, especially once you get complex conjugates and transposers and conjugate transposers all going at the same time. Okay, but the idempotents in the spectral decomposition of a normal matrix are Hermitian. Okay, and if the eigenvalues are real, then the matrix itself is real of any combination of Hermitian matrices is Hermitian. Okay, but in general, normal matrices, the spectral idempotents are Hermitian. Now, that means that we have this. So the complex conjugate of f of s is equal to the transpose of f of s. Okay, now if you look here, we've got a beta comma alpha, and then we've got an alpha comma beta, so there's a transpose hiding there. Now, it takes fewer strokes to write down complex conjugate than it does to write down transpose, so there's a tradition to write this in terms of the complex conjugate. Okay, and so the conclusion is for discrete walks starting on the arc alpha, the average probability I've probably got the alpha and beta in the wrong place here. The average probability of the walkers on the arc beta is given by this. Okay, and so we can define the average mixing matrix of discrete walk to be this. Okay, so that is like the formula we got in the continuous case, but we've got this complex conjugate hiding there, or transpose. Now, okay, so it is what it is. So, but the point is, we get a very similar formula. We're paying a slight price because of the fact that we're dealing with something, well, Hamiltonian is not real in general. And I left the exercise. You can show that m hat is given equal to this limit. Yeah, so we have an explicit formula for m hat, and this is it's into the definition. Any questions at this point? So, it's probably possible to set things up so that I can derive the results for the average mixing matrix of continuous walks and discrete walks all at the same time. It probably wouldn't be fun to watch. And so I'm taking the strategy that it's nice to repeat things in slightly different forms sometimes to try and see what's going on. So the result I'm about to prove is actually true in the continuous case as well, with a fairly similar proof. So the claim is that the average mixing matrix is positive semi-definite. Now, that's not an average state is positive semi-definite because you're averaging a density matrices, and density matrices is positive semi-definite. And although it needs a line or two of proof, an average of positive semi-definite matrices is positive semi-definite. And it doesn't matter whether you compute the average by a weighted sum or by an integral, it's positive semi-definite. So average states are positive semi-definite for free. But m hat is not an average of states. Okay, and so the mixing matrix in the continuous case is not positive semi-definite. But the average mixing matrix is, and the eigenvalues in fact lie in intervals 0 to 1. So in particular, all the eigenvalues are less than 1. Since it's positive semi-definite, they're all at least 0, of course. And I was going on before about bars and transposes, and that's partly because of what's about to come. If f is emission, which it is, then so is f bar. Now, this, of course, gives you a headache, but it's true. And f and f bar have the same eigenvalues because f is emission, the eigenvalues are real. So if u has got the spectral decomposition, then, well, fr is positive semi-definite and fr hat is positive semi-definite. Fr bar, positive semi-definite. By Scher's theorem, or one of the Scher's theorems, the Scher product of two positive semi-definite matrices is positive semi-definite. Okay, and so this is positive semi-definite, and so therefore this sum is positive semi-definite, and so that proves that m hat is positive semi-definite. I mean, this is, in a sense, this sentence here is simple enough, but you sort of need to think a little bit about this. Why they have the same argument is, why is this positive semi-definite? Why is this emission? But there's nothing hiding there. Okay, and as I said, the basic problem is that taking the complex conjugate is not a linear map. And the minute you start dealing with maps that are not linear, your life gets a lot more complicated very quickly. But anyway, so we've established that M hat is quasi-semi-definite. For the second claim, it's we say, well, we've got the identity matrix as the Scherr square of itself, and so the identity is the sum of the idempotencies FR, and equally it's the sum of the complex conjugates of those. And when you expand this out, you get that probably should be an M hat there. You get this is M hat plus a sum of Scherr products of FRs and FS bars. Now, each of these products is quasi-semi-definite by Scherr's theorem, and so the sum is quasi-semi-definite. So I minus M hat is quasi-semi-definite. Okay, and so all the eigenvalues are less than 1. Now, essentially the same proof works when you're doing the continuous case, but this is, so provided you don't get sort of tripped up on the complex conjugates, it's straightforward. Okay, so so we have, I've introduced the average mixing matrix, and so you can view this as kind of an approximation to the long-term behavior of a walk. Now, the quantum walks are not, in general, not periodic. They're all over the place, and they return to anything they're visited once, so they're not settling down to any average. But the average mixing matrix is a substitute for that. So it can be viewed as a substitute for long-term behavior, and so you can try and define parameters in terms of the average mixing matrix. I want to consider another special case, uniform average mixing. So this is where the average mixing matrix is flat. All entries in the average matrix have the same value. Now, the average mixing matrix is, oh, very careful here, is it? No, I won't say anything, then I'll be safe. So yeah, we're going to say a quantum walk has uniform average mixing if M hat is flat. Now, notice that M hat needn't be real in general. Now, one of the current exercises, which is to show that if U is rational, then M hat is rational. Now, if you know a bit of Galois theory, it's not too hard. If you don't know the Galois theory, pick another problem. But it is true that if U is real, rational, then M hat is rational. And so for the arc reversal walk, U is certainly, with the Grover coin, then the U is certainly rational. And so M hat will be rational in that case. Okay. Now, but what I'm saying here is that there's no reason, nothing that forces M hat to be real, even real. And so this definition just says M hat is flat. So the entries might be all over the place, but they all have the same absolute value. And so I want to characterize when the average mixing matrix is flat. Now, in the continuous case, which you'll have all forgotten, we proved that if the average mixing matrix is flat, then the graph says either K1 or K2. Okay, so there wasn't much future in looking at average mixing matrix, uniform average mixing. In the discrete case, that is no longer true, although we're far from understanding or even having a good supply of examples. So I'll start with this following lemma. So I'm going to have a transition matrix n by n, because n is going to appear shortly, with spectral decomposition as usual. And I'm going to use mu sub r to note the multiplicity of the eigenvalue theta of r. Then the claim is that the trace of M hat is less than this. So the sum of the squares of the, now notice R is summed over distinct eigenvalues. There won't be n terms here in general, but the sum of the squares of the multiplicity is divided by n. Okay, so as a lower bound on the trace, we'll be strengthening this shortly, something that's somewhat more useful. And equality holds if and only if each idempotent has constant diagonal. Which would mean that in the terms of the jargon we used before, that the matrix U is walk regular. Any power of U has constant diagonal. Okay, so the stuff we developed before still applies, but the situation is different. Okay, so let's think about this. Well, we have one of them. We take a sum mu r squared. Mu r is just a trace of fr, and I claim that this is equal less than, by Cauchy-Schwarz, this is less than equal to the trace of fr circle fr bar. And so that implies that the trace of m hat, which is this, is greater than or equal to that. Okay, so that's what I said to prove. And equality holds if and only if the, well, equality holds in Cauchy-Schwarz, and from that you deduce that you must have constant diagonal. Now I haven't put in all the details here, and if I try, you want to write out your Cauchy-Schwarz, possibly it's going to probably it'll take a line or two, but that's the guts of the proof. Now the corollary in some sense is more useful. So we have the trace of m hat is always at least 1, and equality holds if and only if the multiplicities are all equal to 1 and each spectral idempotent is flat. Okay. So we have the sum of the multiplicities is equal to n, and so we get 0 is less than equal to this sum of squares. Now, this is actually the variance of the probability density. It takes value UR on n at the point on theta r, but at this we have this, and so I'm using the fact that the well, let's not worry about it. So, but on the other hand, sigma UR is equal to n, so this is sigma UR squared minus 1, and when you expand that, you get that this is equal to sigma UR squared minus n. And so the conclusion is that this is at least 1. And if equality holds, then UR is equal to 1. The eigenvalues are simple. And so F1 is now a rank 1 matrix with constant diagonal. But FR is going to be equal to XX start. And the diagonal entries are just the squares of the entries of X. And so from that you can deduce quickly that that F must be flat. Okay. Now, for continuous walks, as I said, you don't get uniform average mixing on a graph with more than 2 vertices, so we don't have to worry. If you look at walks on oriented graphs, which I didn't discuss, you end up in a similar situation. Actually, maybe I will say something about that. So if you're dealing with oriented graphs, and as a graph where each pair of vertices is either not joined by anything or joined by exactly one arc. So if you have an oriented graph, instead of the adjacency matrix, you'd use a skew adjacency matrix. So it's a 0 plus or minus 1 matrix. Let's call it S, and S transpose is equal to minus S. So it's skew symmetric. Okay, so now the nice thing is that the exponential of T times the skew symmetric is orthogonal, an orthogonal matrix. I think we got orthogonal being used in 3 different meanings. So, but this is an orthogonal matrix, and so it's unitary. And so the point is, this gives us a continuous walk, and we can get all the strange behaviors in these walks that we get in the other cases. We don't need the complex numbers to make things act funny. Okay, and so this gives us, so now we have a continuous walk on an oriented graph. Okay, and we're in a certain sense our life's a little easier because we're dealing with orthogonal matrices, and so our transition matrix is real. Okay, but and so then we can go through and define average mixing and things like this, and we'll get a theorem along these lines. So you can get examples, actual examples where the eigenvalues are simple, and the eigenvalues are simple and the idempotents are flat. Okay, so that can happen in cases. Now, it doesn't happen for the continuous walk with the adjacency matrix of the graph, as a Hamiltonian, or more generally as a Laplacian or weighted sine Laplacian. They're all symmetric and real, so they all behave the same way. Okay, so then we have a characterization of uniform mixing. So for a discrete walk, the following equivalent: the walk has uniform average mixing, trace of M hat is 1, and the eigenvalues of U is simple, and its spectral projections are flat. Okay, so we have a characterization. Now, one thing this suggests is that the trace of M hat is possibly an interesting invariant of the underlying graph. And we've done some computation based on this, but there's no real theory yet. But so the point is that the closer the trace of M hat is equal to 1, the closer you are to uniform average mixing. And so, okay, I prove that. So if we have uniform average mixing, then M hat is equal to 1 on J, and the trace of M hat is equal to 1. So the first A implies B. From the corollary above, you get the B implies C free, and the C holds, M hat is equal to this, and what do I have? That's Bottom-Roll's hypothesis. There's nothing to say to that. Okay. So what's the time? Okay. So as I said, so the theory of mixing extends to the theory of from continuous walks to discrete walks. We have some examples of uniform average mixing, but not many. Okay. So in a certain sense, most of the obvious questions you ask, the answer will be, I don't know yet. Okay. And so, and the mixing is, mixing hasn't been investigated that much, even in the continuous case. And so most of these questions, haven't been considered. And, the relation between properties of the walk and properties of the graph are of interest. Okay. Now, I think what I'll do is I'm going to find it. Yeah. I just want to say a little bit about, I'm going to finish off with a few remarks about discrete walks. And then on Friday, I'm going to start on the quantum homomorphisms and colorings and things. So what I've been talking about is the arc reversal walks. These are a special case of the two reflection walk, and actually essentially a special case of the bipartite walks. So we have that family walks, and the theory we have would work. It works for bipartite walks. Tina Chen did a PhD thesis on this case. Now, one thing you can do, we're assuming when we looked at arc reversal, the underlying graph is regular, but that was just to make our lives easier. You can extend the theory to deal with graphs that aren't regular. In a certain sense, there's no need to, because the physicists can do anything they want with quantum walks using regular graphs anyway, so they don't need to worry about the more general case, but you can do it. There is another class of walks which are not two reflection walks, so I wanted to give you one example of that. So dealing with a deregular digraph, so that means each vertex has d arcs leaving it and d arcs coming in. So sometimes, now a shunt decomposition of a deregular digraph is a set of permutation matrices P1 up to PD whose sum is the adjacency matrix. I don't know why I did that. And so given those shunts, we define this matrix S. Now, if you want to know why you've got inverses in there, you're going to have to ask Harmony, because I don't remember. But we formed this block matrix, okay? Now, it's a permutation matrix. This block is a permutation. And its order is ND by ND, okay? And so that's going to be the analog of the matrix R we were using before. I mean, R was a permutation matrix with 2 by 2 blocks. So this is the analog of R. And we have a coin matrix. And I'm not going to be too particular about the coin matrix at this point, just as D by D unitary. Now, there's something you've got to watch out for there. When I say I'm going to use this particular coin, this particular unitary matrix on this vertex, I have to give you some extra information. I have to tell you which arc on that vertex corresponds to which column of the coin. And if the coin is not a Grover coin, then different choices may give different behavior. So to specify the walk completely, you have to specify the coin, and in particular, an ordering of the arcs on each vertex. Now, at that point, you have something very close to a map, a rotation system. Okay, but my point is that to specify a quantum discrete walk using general coins, just telling us the coins is not enough. You have to tell us how the arcs on a given vertex are assigned to rows and columns of the coin. But leaving that aside for the moment, we'll go on. And so so we have a coin matrix, and so we get a product of 2 matrices. I don't want to do that. We get a product of 2 matrices. This is unitary, so we have a transition matrix. So we get a shunt, what's called a shunt decomposition walk. These were due to Aharonov and others. Now, the point here is, in general, neither S nor C times N have order 2. Okay, so we cannot use the theory that we were working with. Now, the situation's pretty bad. Harmy and I were wasting time at one point where we had basically you had one matrix here of order 2 and another matrix here of order 3. And we basically couldn't make any progress under those assumptions. The problem is that 2 elements of order 2 generate the dihedral group, and an element of order 2 and element of order 3 generate the 2 by 2 invertible matrices over the integers, and that has 3 subgroups, so it's much more complicated than the dihedral group. But we can make a bit of progress, or at least say something mildly interesting. First thing is, if you have a d-regular digraph, it does admit a shunt decomposition. And so I'm going to use some non-trivial graph theory for this first point in this course. If we let B be the adjacency matrix of our directed graph, then we can construct this guy. Now, this is a 0-1 matrix, so A is actually a adjacency matrix of a bipartite graph. It's a d-regular bipartite graph. Now, the theorem we teach the kiddies is if you have a k-regular bipartite graph, it has a 1 factorization. You can color the edges with k colors, so that each vertex is on exactly 1 edge of each color. This is a consequence of Hall's theorem. So you can always find that. So that says there are permutations Q1 to QD, such that the square is equal to identity, and the sum is equal to A. Now, if you've got permutations that sum to A, they have to be 0 on this block and 0 on that block. And so those permutations can be written in this form. There probably should be a transpose there, but let's not worry. And so then these guys give you a shunt decomposition of X. So every d-regular vector graph has a shunt decomposition. Okay, so there are lots of shunt decompositions. They're going to, so the vast numbers. And to finish, as one a complete remark, well, one bipartite graph I could take, one directed graph I'm going to take would be the complete directed graph on n vertices with a loop on each vertex. So the adjacency matrix is the all-once matrix. Then you can show that the shunt decompositions of X correspond to n by n Latin squares. I'll leave that as an exercise. But the n by n Latin square, n by n matrix, each entries 1 through n, each integer occurs exactly once in each row and each column. So it's a sum of n permutation matrices. And so there's your shunt decomposition. And so now for each Latin square, we have attached to it a shunt decomposition walk. Now, no one's ever thought about what you do with these things, and so that's where I'm going to stop with the